Okay, so for the last two lectures, we have covered uh, a model called linear regression model, which is basically you have some p-random p features and also some response variable y, and then you want to fit a linear model on it. And then we have to do some analysis on the parameters and also on the residuals to further analyze some of the behavior of the model. And today we will continue our discussion specifically on doing hypothesis testing on the model parameter, which will kind of give you some information regarding how important or whether this features it is important in your model to predict the response variable or not. So that will be the purpose for the model and also for the for hypothesis testing. Okay, so first let me write down the model. So continue linear regression model, which takes the form of y equal to x beta plus epsilon. And then we have the epsilon following a normal distribution with mean 0 and then sigma square identity with dimension n, where n here is the number of observations in your data. So we also obtain the closed form solution for beta, which is beta hat equal to equal to x transpose x inverse and then x transpose y. Okay, so that means given the data and the response variable, you are able to calculate your estimator for the model, and which is the so that when you have, let's say, a new set of data, and then when you're calculating x beta, you will get your prediction for that new data point. Okay. And then we also talk about the distribution for this parameter, which also following a normal distribution with dimension p or k plus 1, which is the number of features including the intercept in your model. And then the mean value is centered around the true value, and the variance is sigma square x transpose x inverse. Okay, so now we're going to talk about how to do hypothesis testing for a particular beta I. So here the beta hat is a p-dimension vector, and then we are interested in one particular value with the subscript I, and this is a scalar. So now we're just focusing on hypothesis testing on a particular value in this p-dimension vector, and then we are just interested in one of them. Okay, so that will be the topic for now. Okay, so in order to perform hypothesis testing, we always need to know what is the distribution for the beta hat, and then starting from there to see whether we are able to calculate the distribution of something. So in our case, what we really want to test is the following null hypothesis. So beta I without the hat, because we are interested in the true parameter beta. And then we are using the data that we collected to calculate the beta hat, and then we hope that this beta hat can tell us some information regarding the true beta that is without the hat. So when you write down the hypothesis, always write down the parameter without the hat. The hat is coming from the data. The beta hat is always coming from data, and then you want to use that to make some inference regarding the true parameter. So here we write down the null hypothesis that beta I equal to 0. So if we reject the null hypothesis, that means we have some evidence that the beta hat, that the beta I is not going to be 0. that means that beta I in this column vector will play a role in helping you to predict your result y when you have a new data point. But if you do not reject the null hypothesis, that is very likely that that particular features may not provide much information or knowledge in helping you when you input a new data point on your prediction when you want to predict the y for that new prediction. Okay, so that is the reason why we want to do hypothesis testing, to gain some knowledge regarding which features are important to help you to predict with your model. Okay. So now we need to calculate, or we need to know more about what is the distribution for our that enable us to perform hypothesis testing. Okay. So first of all, we know that the beta hat is going to be normal distribution. So maybe you can start from there to see if that can help us to perform hypothesis testing. So first of all, we can do standardization. So beta hat minus the true value. Okay, so basically it's that the random variable minus the mean, and then we can also taking the standard deviation for the covariance. Okay, and then raised to the power of 1/2. So basically this is just doing the standardization. So the beta hat following a multivariate normal, and then you perform this standardization, then this one will follow a normal distribution with 0 and then identity matrix. So just to elaborate a little bit on this, for the scalar version, we usually have x following a normal with mean, mu, and sigma square. And then when you standardize it, you usually do something like x minus mu over sigma. And then this one will follow a normal, standard normal. So this is what we usually do in the scalar version. And here, because these are all p-dimension vector or p by p matrix, so you need to use the vector matrix notations to perform the standardization. But essentially, it's still going to be the same idea. You have the random variable minus the mean value, and then over the standard deviation. But for matrix, you need to raise to the power of negative 1/2 to make it the square root of that, and then also place it in the denominator. So this is just a matrix vector notation for the standardization in this way, or as an extension for the scalar version. Okay, and also in reversely, when you have some random variable z that follow a normal 0, 1, you can also do mu plus the standard deviation plus the z, multiplied by z, and you will get x, and then this x will follow a normal mu sigma square. So this is the reverse process for the standardization. And this one, sometimes people, or in machine learning, people call this reparameterization, which plays an important role in many generative models. So one of the model, which is called variational autoencoder, which is to generating image. One very important reason that the model works in the deep learning to generate image is that we are able to apply this in the deep learning, and that makes it the image generation possible for the variational autoencoder. Okay. But that is just some side notes, and yeah. But what we're really interested is this particular standardization, and then we obtain the standard normal distribution. Okay, so once we have that, maybe we can do one more transformation. So we can do beta hat minus beta, taking the transpose, and then have the variance in the middle. Or maybe just so here just one copy of this, and then let me add another copy. So let me first write down this part. So this one here following a standard normal distribution, just a multivariate version. And now I'm just taking the square. And then this is how people usually write for the matrix vector notation. So this is equivalent when you have z following a standard normal in the scalar version, and then z square, or z multiplied by z, this one following a chi-square distribution degree of freedom 1. So that is the scalar version, and this is essentially the same thing for the multivariate version. So this one follow a standard normal, and then we're just taking the z square, or z transpose z, as the quadratic form. And then this one also following a chi-square distribution. The only difference is that because this is a p-dimension vector, or a normal distribution, so that the chi-square distribution will have a degree of freedom p. But essentially it's the same thing. Here we have the scalar version that we take the z squared, we have a chi-square distribution. Here we just take the quadratic form, and then we also have a chi-square distribution with degree of freedom p. Okay. So this is nothing different from the scalar version, except that just some notation. Okay, once we have that, we can group the things together. Beta hat minus the true value, and then I'm missing another 1/2 here. X transpose X, then beta hat square. So this one follow the chi-square distribution. So yeah, we have some result regarding our parameter, our problem of interest. So here you can consider this beta is our true parameter, and then in our null hypothesis, usually we just, because we set it equal to 0, so when we do the test statistics, it will just minus 0, and then you want to calculate, you want to have some way to calculate the probability that this one deviate from 0, and that will give you the p-value, or that's essentially the idea for hypothesis testing. But by looking at this test statistic, or this formulation for now, you'll find out that it involving one component, which is the sigma square. That is also unknown to us. So with this formulation, for now, we are still not able to perform hypothesis testing. So that means we need to use additional components to handling the denominator, and then to see if we are able to calculate the p-value or from the resulting distribution. Okay, but that is just at least we get something for now, but it's just not enough. So the next step is that we need to take care of the denominator. Okay, so to handle the unknown variance sigma square, we need to do some further analysis, which is the following. So first of all, let's take a look at this formulation. Y minus x beta, then taking the transpose. Sigma square. Okay, So we are going to gain some knowledge from this expression and then to use it to handling the denominator, the unknown variance term, the sigma square. Okay. So also the numerator looks very similar to the residual. So this is also what I mentioned last time, is that the residual will always provide you some useful information regarding how the variance behaves. So this formulation should give us some knowledge regarding the variance, and that should help us to provide some information on the test statistics. Okay, so now let's first analyzing this particular expression. And so to analyze this expression, we can do the following. So we first expanding each of the terms in the parentheses by plus and minus the prediction. So the one with the hat. So here I'm just plus a x beta hat and minus x beta hat. So that does not alter the values in the terms in the parentheses. And then we do the same thing for the second term, as this is the quadratic form. Okay, and now let's also group some of the terms together, and we will have the following. So the y minus one of the term that we introduce, x beta hat here. So the data or the response variables minus the prediction from the model that we learned. And then we have the plus x, and then I'm going to group the beta hat with the true beta here. So this is just the third term minus the second term. So we have the x in the front and then the beta hat minus the true beta. So I'm going to group the terms in this way. And then same thing for the second part. And then for the response variable y minus the prediction, that is what we call the residual. So here is the e, not the epsilon. And then we have the same thing. So now we are back into two terms inside the parentheses. So the e and then the x multiplied by the difference from the beta hat and the beta true. And then let's distribute the terms to get the following. So the first one is the e transpose e over sigma squared. And this is something that we see last time. And the middle term is that you have two copies of e multiplied by that. So you will have this, but later we will show that this is actually just becomes 0. And then we have the quadratic forms. So now we have the first three terms here. And then I'm not sure if I have showed this last time, but maybe I'll just give it as a result so that the E transpose X is actually equal to 0. And then if you want to check on your own, you can consider the E as I minus H multiplied by Y and then multiplied by X. And then you can expand this, and then you can see that it's equal to 0. But I'm just going to write down as a result instead of showing that. Okay, so that means our expansion will give us 2 terms as a result. And later I will explain why we are doing this. Okay, so just to summarize, what we're doing here is that here we first start from this particular expression, and then we perform some manipulation that resulting in the following 2 terms. And now we are just going to further analyzing why this expansion can help us or to provide some useful information to perform hypothesis testing. So first of all, let's take a look at the term that we begin with. So this is the true random variable, or the random variable y minus the x beta. So when we introduce the model, we have the following distribution for y, which is the y is following a normal distribution with dimension n, and then sigma identity. So we know the distribution for y. So for the first term here, this one is just a standardization for the random variable y. You minus the mean and then over the standard deviation, and then you take in the quadratic forms. So that means the left-hand side. So based on the normal distribution, we know that the left-hand side here actually following a chi-square distribution with degree of freedom n. So that is the parts, the terms that we started with on the left-hand side. And now let's take a look on the 2 terms on the right-hand side. So for this one, we still don't know the distribution for the E transpose E over sigma. But after the expansion, we find out that we actually know the distribution for the second term. So that is coming from that the beta hat is following a p-dimension normal distribution centered around the true beta, and then with the covariance sigma square x transpose x inverse. So based on this normal distribution, we know that the second term on the right-hand side also following a chi-square distribution with degree of freedom p here. So now the question is, what is the distribution for the middle part? And also from last time, we showed that the residual is actually independent of the beta hat. This is one of the results that we showed. I think it's from the result 2 from last time, that we showed that the covariance of that, the E and the beta hat, is equal to 0, so that they're independent. So now that we know that the 2 terms on the right-hand side, they are independent. So that means we are able to know that this distribution also going to follow a chi-square distribution, because you need to take one chi-square distribution plus another chi-square independent chi-square random variables to get another chi-square random variables. So we know that the sum of them follow a chi-square one of them follow chi-square, so this one should also follow in chi-square. And then since they are independent. So to get the distribution, or well, we know that it's following chi-square, to get the degree of freedom for this chi-square distribution, one way to do it is to calculate the degree of freedom through the moment generating function. So yeah. So on the left hand side, we have the degree of freedom is n. So the moment generating function is 1 minus 2t with n over 2. And then we also know this one is a chi-square degree of freedom p. So this one has the moment generating function of 1 minus 2t for p over 2. And then for the missing part, we can just do the division. So let me just write down the moment generating function for the, let me give a, maybe just call it q. Okay, so the moment generating function for this one multiplied by the moment generating function, you should get the moment generating function of the left hand side. So that means when you take the division, so when you take this one in the denominator, so that you know the moment generating function, which you already know is going to follow a chi-square, and then the degree of freedom is just negative n minus p over 2. And then the n minus p will give you the degree of freedom. So that means the E transpose E over sigma square should following a chi-square distribution with degree of freedom n minus p, or n minus k plus k minus 1. Yeah. So we go through a lot to calculating this, and now we have enough information to calculate our test statistics. So any question or comments up to this point regarding how do we get the distribution for this E transpose E over sigma square? Okay, so now let's back to our original question of interest, which is we want to test the hypothesis of beta I equal to 0. And then we know that the beta I the beta hat following a normal with the true and that variance. Okay, so first let's do another transformation to get one of the index from your p dimension vector. So here, let's first define a column vector called A, which is defined as a vector of 0, except that the ith entry has a 1. Okay, so let's first define a vector called A, which has the following construction. It's just a 0 column vector, and then only the ith entry is equal to 1. So now, when we perform this multiplication, A transpose beta hat, we are essentially multiplying this row vector with the column vector beta. And then when you multiply these two together, you will just obtain the beta I hat, the ith entry in your p-dimension vector. Okay. The reason why we're introducing this vector A is that we know that the beta is following a normal distribution, and then a linear transformation of a normal random variable also follow a normal random variable, except that it's going to be a scalar version. So that means the A transpose beta I hat is also going to follow a scalar version normal distribution, and then with the mean also A transpose beta. So we're just performing a linear operation to this distribution. So when you multiply A transpose to a normal random variable, you also perform the same matrix vector multiplication to its mean and the covariance. So that the mean for A transpose beta is going to be A transpose beta for the true value. And then for the covariance is that the sigma square, or maybe I group these two together, you will have A transpose and then the original covariance matrix multiplied by A. And then this thing is just a scalar. So if you want, you can also put a dimension 1 here. It's just a scalar version. So the vector of A will help us to extract a particular entry from your column vector, beta 1 to beta p. This one without the I, but this one, you are just extracting one of the entries in a column vector with p dimension. Okay. And then let's give another notation for this one. Okay, so maybe let me also explain a little bit on this one. So you essentially have a 0 vector with only the ith entry equal to 1 multiplied by some, let's say, sigma matrix, and then sigma 2, 1, sigma p1, and then same thing here. So you have a p-dimension square matrix and then a column vector which also have a 1 in that. So when you're expanding these terms here, when you doing this A transpose sigma A, what you're doing is actually just getting the ith entry in the main diagonal. So we can give a name to this one, which is the sigma square and then VII. Here the VII is just referring to the ith entry of the X transpose X inverse. So let me just repeat what this operation doing here is that when you left multiply a vector A, which takes a zero vector with only the ith entry equal to 1, and then you also have an A here, that is essentially just extracting the II entry in this p by p matrix. So if you want to try it, you can just expanding the term here. You will see that your result is just going to be the entry, the ith entry in this matrix here. Okay, so we're just giving a name which is called VII, which is referring to the ith entry or the ith elements in the main diagonal. But essentially just some numeric tools to help you to get that particular elements from that matrix. Okay. So now let's clean up some note. We have the beta I hat following a normal distribution. And then also the same thing here. You are just getting the ith element in the true value. So you're also getting the beta I here without. And then you have the sigma square VII, where VII is just the I entry of X transpose X inverse. So when you left and right multiply by that vector A, you are essentially just getting that particular entry that you want. And then here everything is in scalar. So this is also a scalar, and then after you multiply by that, you will also get a scalar. Okay. Okay, so now let's bring all the components together, and then you will see how this one will help you to perform the hypothesis testing. So again, let's standardize it, and then taking the square root of the covariance of the variance. So standardizing like that, and this one will follow a normal standard normal 0 and 1 in the scalar version. Okay, and now let's bring in the component that we just calculated regarding the variance. Which is the E transpose E over sigma square. So this is coming from this part, where we go through the expansion, and then using the homogeneous function, we know that this one following a chi-square distribution, degree of freedom n minus p. Okay, so now we bring that component into the picture. So we know that this one following a chi-square distribution, degree of freedom p minus n minus p. Okay, and then we divide it by its own degree of freedom, and then taking the square root. So now this whole thing here will follow a t distribution, as well. We have from very early we kind of proved that when you perform this kind of transformation, you will get a t distribution, and then the degree of freedom is n minus p. Okay. So after all these transformation, let's check, does this test statistic or this formulation allows us to perform hypothesis testing or not? So here, the beta I hat is actually calculated from your data, or you can use the closed form solution, the X transpose X inverse X transpose Y, to get that. And then the beta I, the true value, under the null hypothesis, the true value equal to 0. So this one has been set to 0. And then the VII is actually coming from the ith entry from this part here. But this one only involving data. So that means you are able to get the ith entry from your data. And now the residual E is actually coming from Y minus X beta. You have this one observed, and also the X as data, and then the beta hat is also calculated from solution. So that means the E can also be calculated. And then you also know the degree of freedom. So the only trick here is that the variance that you don't know at the beginning will cancel out with the variance in the denominator, so that after they canceled, so you don't need to worry about the variance that you don't know from this distribution. So from here, because you don't know the true variance, so that's why you are not able to use the chi-square distribution to perform hypothesis testing. But after we analyzing this particular expression, and then we obtain that this part following a chi-square distribution, and then using that additional information, into the whole picture, you are able to using t-distribution to perform hypothesis testing. So now that when you plug in 0 and then everything calculated from data, and then you can calculate the p-value that the beta I is not not equal to 0, not equal to 0 because the hypothesis is setting the beta I equal to 0. So you are able to calculating the p-value from the t distribution. Basically, you have the two-sided, and that will serve as your p-value for your beta I not equal to 0. And then from there, you have the statistical power to claim that whether you want to reject or not reject the null hypothesis. So if that p-value is lower than 0.05, then you reject the null hypothesis, and then you can say that that particular feature I will play an important role in your model to predict the output Y. And then if you are not able to reject the null hypothesis, that means you have some statistical evidence to say that that particular feature may not play an important role in your prediction. So for your future analysis, maybe you want to remove that particular features in your model, and that is just a different story. But by analyzing all these terms and using the t-distribution, you are able to perform hypothesis testing. Okay, so that should give you the reasoning and also how to perform hypothesis testing from the t-distribution instead of using chi-square distribution. Okay, any question or comments? If there's no other question, then let me just cover one last topic, and that will conclude our discourse. So the next topic is called constrained linear regression. Okay, so like the name is saying, is that we want to solve a linear regression model from your data. You want to fit the model to your data, but with some constraint. So to state the constraint mathematically, what we really want is that the beta hat, and now with a subscript C, stand for the constraint. And then we want to minimize our sum of square residual, that objective function. So y minus x beta transpose that. So if you just perform this minimization, you will get the ordinary or the maximum or the ordinary least square estimator, which will give you the x transpose x inverse x transpose y. So if you just do that. But now we added one more additional constraint to this framework. So we write it as subject to that C beta is equal to gamma. So here the C is a M by P matrix. And then the beta is just a P by 1 vector. and also the gamma here, it's a n by 1 vector. So when you multiply a matrix n by p with a p by 1 vector, you will obtain a n by 1 vector. Okay, so the constraint is coming from the idea. So not only you want to fit a model to learn the beta from a data, and also you want to impose some constraint to the coefficient. So here you can think of the C as you want that. Let me just make up one example. So you can have like 0, 0, 1, 0, 2, 0. So suppose you have like a 4, maybe -1 and then 0, 0. So suppose this is your matrix C, and then you have a 6 dimension for your coefficient. That means you have 6 features that you collect from your data, that you collected the data that you want to predict the y. So you not only want to fit a model with these 6 features, and you also assume that maybe the 3rd feature and the 4th and the 5th features, they have some relation between those features. So for example, in some like gene studies, some of the genes are related to each other. So this is saying that your beta 3 plus 2 copies of the beta 5 is equal to, let's say the gamma is 2 and 1 is equal to 2. And this one is saying that the beta 2 minus the beta 4 should be equal to 1. So this will serve as your gamma. Okay, so that means you not only want to fit a model beta with your data x and y, but you also imposing some of the constraint which you think that are important to as a domain expert. So this is just an additional constraint that you impose on the coefficient. So this is called a constraint optimization, and that is also the name for the constraint linear regression. You not only want to fit a linear regression model, but you also imposing some constraint on the coefficient, because as the domain expert, you think that there's some relationship between the features or the data that you collected. So that is the idea for the constraint optimization. Okay, so let's say this is your matrix C, and this is your matrix vector gamma. Okay. Okay. So, yeah, just to reiterate again, you not only want to fit a linear regression model, but you also think that there's some relationship between the features. So that's why you added an additional constraint to your linear regression model. So that is called constraint linear regression model. Okay. So the next question is regarding how to solve this kind of mathematical problem. And in mathematics, there's a way called Lagrangian, and which is referring to the following. So the name is called Lagrangian, and this is a very important concept in optimization. So the Lagrangian is defined as the following. So I write it as a capital L with the parameter of interest, because you want to solve the beta. So you have to put the beta in the parenthesis. And the Lagrangian is defined as the following, which is the y minus x beta transpose, and then y minus x beta. So this is coming from the original part, the original objective function here. Okay, So part of the Lagrangian is coming from the objective function here. But we are solving a constraint optimization problem. So you also want to introduce the constraint into the framework. So the Lagrangian is referring to the original problem and then plus a Lagrange multiplier with the constraint here. So the constraint is that C multiplied by beta equal to gamma. And then for the constraint, you need to write it as C beta minus gamma equal to 0. And this part will serve as the constraint that you want to input into the objective function. So that the overall idea is that the Lagrangian is a connection between your original problem here and also with the constraint. So you group the objective function or the original problem with the constraint all together into a framework, and then you want to solve this simultaneously, and then the optimizer or the beta that you obtain by solving this objective function will satisfy not only minimizing the original problem but also satisfying this constraint. So the Lagrangian is a bridge between your original problem and the constraint. And after you're solving that, the beta that you get will not only minimize this part, but will also satisfying this constraint. So that is the role of the Lagrangian. And this is a very, very important concept in optimization. So if you go to grad school, optimization is a very, very important thing in statistics and also in many machine learning. Or personally, I would say in deep learning, everything is about optimization. All those ChatGPT, all those variation autoencoder, everything is you solve by performing optimization on the parameter. So this is just a very simple version for a linear regression model. But when you're training the ChatGPT or training like the VAE for image, nothing different from performing optimization. It's essentially the same thing. Okay. So to me, deep learning or machine learning, they're all just about optimization. And this Lagrangian is just one way to solve the constraint optimization problem. Okay, so now we set up the Lagrangian. The next step will just be the standard procedure. So you just need to take the derivative with respect to the parameter of interest. So first order derivative for this Lagrangian. Okay, so this part is nothing different from the linear regression model. So you will still have the result from when we solve the linear regression model. And now I'm just going to write down without showing some of the details. So you have 2 times the x transpose y, and then plus 2 copies of x transpose x beta. So this part is the same as how you solve the original or the linear regression model part. The only difference is that you need to take care of this constraint because the Lagrangian bridge between the original problem and the constraint altogether. Okay. So for the second part, also here, let me just add a coefficient here, the 2. You can consider the 2 lambda altogether as a Lagrange multiplier. So you can always add any coefficient that you want in the front. And then here I'm just going to add a 2 because later it will help us to cancel out some of the terms. So, but you can choose any number here for your convenience. Okay, and then after you take the derivative with respect to beta, you only have 2 times. And then now I'm going to change the order C transpose lambda. So the reason I'm changing the order is just because I want to match all the dimension together here. So if you want to check, this is p by n, and then this is n by 1. So you have a p by 1 vector here. Here you have a p by p, and then p by 1. You also have a p by 1 vector. And then here you have a p by m, and then m by 1. So you would get a p by 1 vector here. So for matrix vector derivatives, the only thing that you want to keep in mind is just to match all the dimension correctly. So for example, here we have all the p by 1 dimensions. So that's the only thing you want to make sure that they all align together. Yeah. So for the scalar version, they are all just scalar, so you don't need to worry about that. But when you go to multivariate, multiple dimensions, that's the only thing you want to keep in mind. So, here we did it correctly, so we have all the p by 1 vector. Okay. So once you set that equal to 0, and then your result for the beta hat with a subscript c as a constraint will be the following. So x transpose x inverse, and then x transpose y minus c transpose lambda. Okay, so that is the solution at this stage. However, this particular expression involving the Lagrange multiplier, which you still don't know what is the value for the Lagrange multiplier. So this cannot serve as your final result. So you need to further analyzing this particular Lagrange multiplier. And once you have a solution for that, and then when you plug into this expression, you will have your final solution for your constraint estimator here. Because you don't know the lambda, what do you call it? The lambda, yes. Because you don't know what the lambda value is, so you don't know your final solution. So this is not a final solution. So we need to further analyzing these terms here. Okay. One thing that we know is that the C multiplied by this constraint estimator should equal to the gamma, because this one has to satisfy, otherwise it is not a constraint estimator. Because we wanted to solve this beta c hat to satisfy this, so we need to kind of like making sure that it satisfies of that. And this equation actually will help us to calculate what is the value for the lambda, and then once we plug in the lambda here, you will get your final answer for this beta hat constraint or beta hat c here. Okay, so now we are going to use this one to guide us to calculating the lambda here. Okay, so this has to be true because we need the constraint to satisfy. Okay, and this one will also means that the c multiply by this one here, the x transpose x inverse, and then x transpose y, and okay, let me also group this one here. So then you have the c multiply by x transpose x inverse, and then the c transpose from here, and then lambda. So here I'm just going to multiply by c to this expression here. So you have c multiplied by this part multiplied by x transpose y. And then the second part is that c multiplied by this part multiplied by here. Okay, so you have two terms. And this one need to satisfy. So it need to be equal to gamma. Okay. So now we need to rearrange the term, and then we just want to get the lambda equal to something here. So we need to solve for this expression. And then we plug in the lambda into here, and that will give us our final expression So that will be what we're going to do next. Okay, so now let's solve for lambda from this expression here. So just to simplify that, you will have the c multiplied by the ordinary, or the least square estimator. So this one without the subscript c, because this is just your closed form solution from the ordinary least square without the constraint. And then minus the c x inverse c transpose lambda. Okay, so now we are interested in that, in the lambda, so let's just think about how we can bring that one out to get an expression for lambda. So this equation means we also have the following holds. So c that multiplied by lambda is equal to c beta hat minus gamma. So this one is without the constraint. Okay, so make sure that you don't put a c here. This is your least square estimator without the constraint here. Okay, and then you have your final solution for the lambda. So the lambda is equal to the following. So this is a matrix, so that when you take the division on the right hand side, you need to use the matrix inverse instead of just putting in the denominator, because it's just not a number anymore. And then c beta hat minus gamma. Okay, so at this stage we have a closed form solution for the Lagrange multiplier, the lambda. So the c is coming from a constraint, the x is coming from your data, and then the beta is also a function of your x and y. So that means you are also able to calculate, and the gamma is also coming from a constraint. So that means everything on the right hand side can give you a result, or can give you a solution, so that nothing on the right hand side is unknown anymore. So now we're going to plug in this lambda back into this solution, and that means this expression will not involving anything that you don't know. Okay, so that means everything on the right hand side after you plug in the lambda will have a closed form solution when you plug in all the components into this expression. Okay, so to plug in lambda into beta c hat, you will have maybe let me give one more transformation for this one. So here let me also expanding this as the beta hat without the constraint, because x transpose x inverse x transpose y, this is the beta hat, and then minus the x transpose x inverse c transpose lambda. So now I'm going to plug in the solution that we find for lambda in here, and then the right hand side for your solution of beta hat with a subscript c will no longer involve anything that you don't know. Okay, so that means the beta hat c is equal to beta hat minus x transpose x inverse c transpose. Okay, that's here. And now let's bring in the solution for lambda. Okay, So that is your final solution for the constraint estimator. So just comments on this is that sometimes you want to solve a constraint optimization problem, but the result, if you just want to, even if you want to just satisfy like in this case a very simple constraint, which is just a linear constraint, c beta equal to gamma, you will see that it actually the solution can be very difficult or can be very complex. So just in practice, when you want to adding some constraint to your problems, things can go very ugly. So just to keep that in mind, it can be very difficult, even when you just want to satisfy a very simple constraint. The things or even the math can be very difficult to solve. Okay. But either way, everything on the right hand side is given. So that means you are able to get a solution for your constraint optimization or your constraint estimate. So let me provide one final remark regarding this, is that how we perform hypothesis testing for the constraint. So C beta equal to gamma. So the following is regarding how we want to perform, or how to perform the hypothesis testing regarding the constraint that you impose. So maybe just going back to the gene examples. So maybe you think that I'm just picking this up. So maybe you think that the third genes are kind of related or has some association with the fifth genes, or in some ways. So how do you perform hypothesis testing to see that whether your hypothesis makes sense or not, or maybe you want to reject that hypothesis or not? So that is what we are going to do here. And then again, we need to know the distribution for this. So whenever you want to perform hypothesis testing, you always need to know the distribution for your parameter of interest. So in this case, it's the C multiplied by beta. Okay, so I'll just provide a few results, and then that will conclude our discussion here. Okay, so again, the first thing is always, or very often, to find the distribution is always related to residual. So the residual plays like what I said last time, the residual plays a very important role in in providing the information that is not provided by a model. So the residual is the part that is not explained by a model. Those part that does not explain by a model will actually give you lots of information regarding the variation, or in our case, it's the sigma square, as what we see earlier. So so very often, you always want to work with the residual. Okay, so here I also add a subscript C here. It's referring to the residual under the constraint model, which is just the y minus the x multiplied by beta hat, but also with a constraint. So this is the beta hat with a subscript C that I plug in here. Okay. So this is the residual under the constraint model. And then if you plug in this expression here, let me just, I will let you to verify if you want. Here I'm just providing the result. So the residual under the constraint model is actually equal to the residual under the unconstrained model plus the following, which is a very long expression. So this is the residual under the constraint model. And now we are going to get some information regarding distribution from this. And there's also another very important concept, which is called the sum of square residual. So here I'm just going to use SSE. And then here I'm using C is referring to the sum of square of the residual under the constraint model. And then you will also have a sum of square residual under the unconstrained model. So this is just the E transpose EC. So just taking the square and then sum them together. So when you take the inner product, or the E transpose E, that's the square, and then you sum them together. So that is the sum of the square residual. And then for this one, it's just the E transpose E. So you square them and then you sum them together. So it's the sum of the square of the residual. So SSE. Okay. And yeah, so this one will actually provide some useful information regarding the distribution. Okay. Let's see. Okay. So yeah, I think I'm going to not going over the details, but I'm just going to give you the solution. So I'm taking the transpose of this one, this expression here. So we need to plug in this term here and then minus that, so that, let me just providing the final answer. So SSC minus SSE without the C is equal to C beta hat minus gamma. So that is the final solution for that. And then also for the okay, so that would be the final solution. And let's see how this is going to perform or provide some distributions or knowledge about the distribution for our constraint. So C beta hat minus gamma. And we know that, so again, we know that beta hat follow normal with the true mean and this covariance. And again, C beta hat minus gamma is nothing but a linear transformation of a normal random variables. So that means this part have a normal distribution with the true value C beta minus gamma. And then the covariance is equal to the sigma square. C x transpose x inverse C transpose. Okay. So now that we know that this is this distribution, or the C minus beta minus gamma following distribution, and then now we can discuss the null hypothesis. So you want to test whether, let's say, particular features, they are related or not. For example, like the second gene or the fifth genes are related or not. And you are essentially testing that the C multiplied by beta minus the gamma equal to 0. So that is your null hypothesis. So that means this part under your null hypothesis is centered around the 0. So that means you have the following. So again, C beta hat minus gamma. And then here you want to minus a 0, because under the null hypothesis, you minus the mean. So you minus a 0 here. And then you perform the standardization again. The inverse, and then C beta hat minus the gamma over sigma square. So this one follow a normal distribution, and now you're just performing the standardization and then taking the square. So that means this one follow a chi-square distribution, and this is with degree of freedom m, because this one is a m-dimension multivariate normal. Okay, and also this one is just the sum of square residual constraint minus the sum of square residual under the unconstrained model. Okay, so now you have this distribution, but again, you don't know what is the variance, the sigma square. So you need to take care of that, but we already showed the proof. So the E transpose E over sigma square following a chi-square distribution with degree of freedom n minus k minus 1, or n minus p if you want. So now that we have these two components, and then when we take the ratio again, the idea follows as you cancel out the parts that you don't know, and then whatever remaining can all be calculated from your data. So that is the overall idea. So now let's take the division and bring everything together. You will have the following. So when you take the division, so basically the sigma square in the denominator on the top, on this term, will cancel out with the sigma square in of this one. So that means you will have the SSE constraint minus the SSE over the SSE. So this part, following a chi-square distribution degree of freedom m. And they divided by the degree of freedom m for that, and then divided by the degree of freedom n minus k minus 1. So you have a chi-square random variable divided by its own degree of freedom on the numerator. You have another chi-square random variable divided by its own degree of freedom. And then by construction, you have a F distribution, degree of freedom m by n minus k minus 1. And then this distribution will now allows you to perform hypothesis testing regarding this hypothesis, this linear constraint here. So now that you have a distribution that allows you to perform the hypothesis. Okay, so just to summarize before I end this lecture, so the idea for this lecture is to provide you the statistical reasoning why we are able to perform hypothesis testing for the beta I for the linear regression model without the constraint. So we first know that this one follows a chi-square distribution, but one of the component is unknown, so we're not able to perform hypothesis testing. That's why we need to calculating to know the distribution for this particular terms. And then we borrow the idea, or we borrow the distribution from T distribution to calculate the p-values, or to reject or not reject the null hypothesis. And then we talk about another constraint linear regression, which is that you not only want to fit a model, but also want to satisfy some of the constraint here. And then for this one, when you want to perform hypothesis testing, also the chi-square distribution itself involving the sigma square that you don't know, so you're not able to do it. And then again, we borrow this part, which we know it also follows a chi-square. And then by taking the division, the parts that we don't know cancel out, and then resulting in a F distribution. And then this will allows us to calculating the p-values and then to reject or not reject the null hypothesis. So we are just doing lots of manipulation and borrow different distribution to achieve the distribution for the test statistics, and that allows you to perform the hypothesis testing. Okay, so I think I will just stop here.